On 3.3 lessons, we're going to discuss the common ion effect. So let's review what would happen if we just do things sort of normally. We put calcium hydroxide into water and some amount will dissolve. And how much? Well, two of these and one of those, so we'll get some amount and double that amount here. And so the molar solubility, or the value of S, will be then K equals, again, 4S cubed, and we divide by 4 and take the cube root, and we find S. So here's our standard molar solubility for calcium hydroxide at the certain temperature. Notice they didn't bother to mention, but I assume it's 25 degrees Celsius. As long as we don't change it, it doesn't matter, because then all this stuff will be true. So is that basic or acidic? Well, it's been dosed in extra OH minus, so this is a basic solution. Suppose some acid were added, though, what would happen? Well, the H pluses available from the acid would meet up with the OH minuses swimming around, the extra ones, in the water, and we'd form water. Now that would reduce the number of these, wouldn't it? We've increased them here, but from that value, we've then decreased it by chewing them up with acid. So with the solubility of the solid, they mean here, increase or decrease. So we've saturated this solution, and this is achieved as much dissolving as it can get. So admittedly, this is extra OH minus by the water's normal standards, pure water's normal standards, but it's the right amount for this dissolving. Right? It's achieved what it can, and it's stopped dissolving because these are the top molarities it can achieve at this temperature. Now, if you're going to add acid, you're going to chew up some of these, and this amount is going to go down. So mathematically, what's going to happen? This thing's always trying to dissolve. In fact, it was dissolving. It was just in equilibrium with the redepositing of the solid. So some of this was always leaving. So what's going to happen to the rate of the deposition of the solid if you start chewing this up? The rate of the reaction to the left is going to decrease as you reduce the molarity of this by adding acid and chewing these up and making them into water. So this reaction is going to shift to the right. And also, by Le Chatelier's principle, using the acid takes some of these out of play. You've weakened the right side. Which way does the reaction shift? It shifts to the right. So the solubility of the solid increases because you've decreased the power of the right side by removing something it needs. So if something reacts with a dissolved ion, and they mean removes it from play, binds it up, that's going to increase the solubility. It doesn't have to be acid-base. If we put in another ion that likes to bind to OH minus, that also removes it from play of combining with the calcium, doesn't it? So if we put in something like X, and it likes to make XOH, then this binding here removes some of this from play, and the leftward reaction is decreased in power, and overall this thing shifts to the right, and the solubility of the solid increases. Now, on this bullet, suppose it were placed in a basic solution. So if you place this in something where this is already elevated, you've increased this number artificially already, and so when this tries to dissolve, remember, it can only achieve K, right? And it's going to hit that number faster if this number is already larger. If you multiply this value, pretend it's like it's trying to achieve, essentially like 2S, right? But you dose it with a kabillion OH minuses first, it can only increase the OH value to double what this number is, right? That's all it can achieve. So if you give it a bunch of OH minus first, it's going to achieve double this number much faster, which means it uses less of this. K is achieved faster when you already supply some of the right side. So the molar solubility decreases when you do that, and that's the common ion effect. So when an ion of the salt is already present, the solubility decreases. On page 2, let's actually do the math for the common ion effect. So if you dose this ahead of time with sodium hydroxide, that's a strong base, and plus the sodium always tries to come off its anion. So either way you look at it, you get OH minus molarity is 0.15. Now that's achieved before we even put the solid in. So the starting amount The starting molarity for OH minus is not 0. That's the point. Hit pause and have a think about that or something. This is the starting molarity of OH minus before you put the solid in. And so then the solid dissolves in a ratio of 2 to 1, so we get these as our equilibrium values. So what's the question? Calculate the molar solubility, which is S. So let's put these values in for our molarities in the KSP expression. Don't forget this one is squared, but that is going to set up a situation where we have to use the quadratic formula. And again, that is not required on the real test. So what we're going to do is assume that with a KSP of something this small, then we can assume that adding the amount of dissolved ion to the amount already pre-existing is so small that we can, in effect, just ignore it. And that lets us squirrel out of using the quadratic formula. Again, with a small KSP like this compared to that beginning molarity, let's say that the amount added by the dissolving is so small that by the time we get done rounding back to significant figures, it won't mathematically matter. So let's just skip it. If it doesn't matter, it doesn't matter. So I'm going to cross it out, and then I can solve for S. So you assume 2S is much, much smaller than 0.15, and so that's why I get to cross it out. So what happened? Let's compare the solubilities. So here's the molar solubility with it dosed, and here's the molar solubility with it undosed. And remember, this is a much bigger number, so it's in the range of 100 times bigger with it undosed. The solubility is much stronger, a much higher number with in pure water when we don't than when we don't dose it. So let's compare the solubility when we dose it with when we don't. And here's the molar solubility when we don't dose it, and here's when we do. And this number is much smaller by range of in the neighborhood of a factor of 100. On example 3, we're going to dose our reaction here previous to putting in the solid with sodium chloride, and all the sodiums come off and leave the chlorides alone. So the chloride ion molarity is this. It's not 0. It's this before you even put in the solid. So the solid dissolves and creates one of these and 2 of those. And these are our equilibrium molarities once it gets done dissolving. So we put these in. However, this is going to be squared here, and that's going to give me a quadratic formula type situation. And what I'm going to do is what I said before, and I'm going to assume that with a KSP this small, the amount that of the chloride ion that's achieved from the actual dissolving is so small compared to the 0.1 molarity that was already there that I can effectively ignore it. So I'm going to cross it out and say forget it because it won't matter by the time I get done anyway, so there's no real point. That lets me out of the quadratic formula. See, assume 2S is much, much smaller than 0.1 to the point where I can just cross it out. Then I solve for S, and that's the molar solubility. So what would it have been in pure water when I start with 0? So I'm going to mentally say, oh, okay, this time this is 0, this is 2S, so I just end up with 2S here. And I'm back to this really kind of common form where I get 4S cubed. Here's my KSP. I divide by 4 and take the cube root. And here's my molar solubility for pure water. And here it is with it dosed. And so it's actually literally 10 times smaller with it pre-dosed in this amount. So increasing the ion of the products before I put in the solid decreases the molar solubility. For the bottom part, I would take a moment and really read this through, and it might take 3 times and so forth, but they do expect that you can solve this kind of problem. It might actually come up. So we have these ions, both at this molarity. Now you start dribbling in this, and what you're doing effectively is adding the sulfate because we know that the sodium comes off. So the sulfate could be adding to either, or it's actually trying to add to both of these cations here. So which precipitates first? Well, the one that precipitates first is the one that needs the less sulfate to hit the value of K. And I would write that down or something. The first one that precipitates is the one that needs the least amount of sulfate such that the K value is generated, because when K is true, then equilibrium has been established, and that's the maximum amount of molarity that can be achieved, and that's a saturated solution. All those are the same thing. The maximum amount of ions that can be achieved And when K is true, or when the current situation Q is the same as K, when Q has reached K, and that's a saturated solution. That's all the same situation. So if K were true, that's where you would have a saturated solution. And if you try to push it just a tiny bit farther, it will not do it, and it will start precipitating. So the maximum proportions here that can be achieved are such that K is true. So if K is true, and if the sulfate is this, the calcium ion is this, what would the sulfate be? If K is true, and that's the calcium concentration, back from here, what sulfate value would need to be achieved to make K be true and start the precipitation? And this is the value. So if this is the lead 2 concentration given at the beginning, what value of sulfate ion would need to be achieved such that it reaches its K value, and this is the sulfate ion concentration? Well, logically, the one that needs the least sulfate will do the precipitating first, and that's going to be the lead ion, because this is much smaller than that. So the lead sulfate will precipitate first. For part B, it took me a moment to even realize what they were asking. But they're asking, now this one's going to precipitate first. What will the lead ion concentration be when this one starts precipitating later? Well, when this starts to precipitate, K will be true, and it can't precipitate until the sulfite ion concentration reaches this. So this will start to precipitate when the sulfate ion concentration hits that. At that point, it reaches K and starts to precipitate. What would the lead ion concentration be when this is true, when this starts to precipitate? So let's borrow this and say, fine, when this starts to precipitate, this sulfite ion concentration will be true. And let's put that in here. And what would the lead ion concentration be at that point? Because I know that K must be true, K must be maintained, and unless you're going to put in less than the required amounts of ion to reach K, but we know we've already exceeded that. We're already pushing way past that, because this already started precipitating and we kept dosing it with sulfate ion. So it can't be true that we're not exceeding K. We're exceeding it every time we drip in more of this. So we're in a saturated solution situation because we keep dripping in more of this, and we just keep creating more and more precipitate of this. So when sulfate ion finally reaches this amount, what will PB be? Well, it reaches this amount and K is true, therefore divide, and we get the lead ion concentration when sulfate ion is high enough to start this one precipitating.